Alright, I just wanted to talk about this problem I had for this logic puzzle I was given a long time ago that I didn't this was an assignment in my computer science course, and I did not figure out the logic solution back then. I figured it out much later, and then the solution is so memorable. It just keeps coming back to me, and like every now and then, and I think about this problem a lot. I've been thinking about it again, and I just like this puzzle so much, I decided to make an explanation discussing the solution. Now, there are many videos discussing the solution already. They're probably better, you can go ahead and watch them, but I wanted to talk about it. So this is the puzzle. Essentially, you have, it's a warden and prisoner solution puzzle. You know, you've got a warden and you've got prisoners, and if the prisoners solve it, they get to leave, and if they don't, they're locked up forever or whatever. Anyway, so the puzzle is as follows. The warden has a chessboard with 64 squares, because that's what a chessboard is, and on each square is a coin. It's either heads up or tails up. Doesn't really matter. One of them is going to be count as face up, one is face down. That doesn't really matter. You can decide between the two prisoners yourselves. Now, there's going to be heads or tails, 64 coins, and the warden will tell them a number between 1 and 64. In some variation of the problem, this square, that the number that he's giving prisoner 1 is going to be a compartment with a key in it, or whatever. It doesn't matter. He's given a number between 1 and 64, and he must choose a single coin to flip. After he flips that coin, he leaves the room, and prisoner 2 enters. There's no communication between the two. Prisoner 2 enters the room, and looking at the board, he must now figure out or tell the warden what number the warden gave to prisoner 1. You can pause and think about this yourself if you don't already know the answer. And if you haven't, here's how the solution works. If my method of explanation works for you, it may not. Anyways, the solution for this is correspondent to a famous storage efficient error checking method in computer science, but it doesn't matter. We're not talking about that right now. Now, this solution obviously has two distinct algorithms that are required. One, that we need to first translate a board into a number consistently, and then figure out which coin to flip. Now, the same board must always give the same number, and every board must represent only a number between 1 and 64, and allow us to turn any number from 1 to 64 into any other number using a single coin. There we go. So that's essentially the core of the problem. Now we're gonna talk about the solution. I'm gonna pull up Paint so I can discuss it. So we'll start with the base case, which is a single coin. And now we're gonna designate either heads or tails as face up, and we will be replacing heads and tails with ones and zeros. So let's say heads is 1 and tails is 0, then whatever, right? So let's say this is a 1 or a 0. It doesn't matter, because there's only one square. You're going to be given a number from 1 to 1. Prisoner 1 will always flip this coin regardless of whether it's heads up or tails up, and prisoner 2 will always give the answer 1. There's only one square. So the state of this coin does not matter. Now we're going to be using binary strings to represent numbers. To understand binary, it's very simple. 1 is 1, 1 0 is 2, 1 1 is 3, and 1 0 0 is 4, and so on. It is base 2. To add binary numbers, it's going to work similarly, but there's going to be a unique form of addition we're adding here. They are essentially modular addition, which means we do not take in excess of the digits represented. So if we add 1 0 0 and 0 1 1, it will equal 1 1 1. This is normal addition. However, because this is binary, we're going to be having a similar form of addition. This is essentially the same as subtraction, that we're finding the difference. We are flipping bits. In other words, 1 plus 1 equals 0, as you can see here. And if we ignore all other digits, we are adding them in a single column. This allows us to keep the number between 1 and 64, keep it consistent, and it becomes scalable, and it lets any coin turn or any number turn into any other number using a single coin. That's what allows us to do it. So this addition, we will only be looking at one digit at a time. So when we add 0 and 1, it will equal to 1. When we add 1 and 1, it will equal to 0. So 1 plus 1 equals 0. 1 plus 0 equals 1, and 0 plus 0 equals 1. Or 0 plus 0 equals 0. So 1, 1, 1 plus 1, 1, 1 equals 0, 0, 0. 1, 1, 1 plus 1, 1, 0 equals 0, 0, 1. If this is one of the core principles, we are going to be doing bit flipping addition. Now, one more detail. We are going to be representing this as 0 to 63 instead of 1 to 64. And then we're going to simply add 1. This does make it a little more convoluted when it comes to thinking about it. It's an extra step, but when programming the solution, I know it's a logic puzzle, I know, but it does make it easier to work with binary quite a bit, because 1 to 4 becomes 0, 0 to 1, 1 instead of 0, 1, 2, 1, 0, 0. This is very important. We keep it at these represent, so for example 0, 0, 0, 1, 1, 0, 1, 1 will be the numbers 1 to 4. This makes things a lot easier to work with, and it makes particular sense for why the first square is worthless. So at 1 square we have no digits. The answer is always 1, or 0, right? In binary it's 0. We don't need anything to represent it. Now, when we have a second square, we see that by going 0 to 1 instead of 1 to 2, we only need a single digit, which is 0 or 1. A single binary digit can represent any answer. Now, how do we know this? They're simply going to be representing the state of this square to whatever the answer is. So if this is 1, the answer is 1 or 2, right? So if this coin is 1, then the prisoner 2 will say 2. If this coin is 0, the prisoner 2 will say 0. So in other words, let's say if this is 1 and the warden gives you 2, you flip the first coin because this board reads 1. You flip it, it still reads 1. The prisoner 2 walks in, says 2. And if this reads 0, the warden says 2. You flip this coin, it becomes 1. And then prisoner 2 walks in, says 2. If this reads 1 and the warden says 1, you flip this coin, it becomes 0. Prisoner 2 walks in, says 1, right? If we're following along so far, great. Now, as we see, this is worthless. So now, once we extend this square, we have to actually use a formula now. Let's say this is 1, this is 0, and this is 1. How do we extend this? Now, first of all, we discussed that numbers 1 through 4 will be represented as these numbers, right? So that means we're going to be adding every single square that reads 1. This square represents 1, or 0, 1, because we have 2 digits now. This square represents 1, 0, and this square represents 1, 1. So similar to this matrix right here. Because these are the only ones with the value of 1, or heads up, or whatever, we will only add these 2 numbers. Because this is a 0, we will not be adding this number. And now 0, 1 plus 1, 1 equals 1, 0, because this equals 0, this equals 1. Now, this reads 2 in binary, or 3, because let's say, you know, this represents this square, which represents 1, 0. And we will be prisoner 2, or if prisoner 2 was looking at this board, he would tell the warden 3. Now, if the warden gives prisoner 1 this board state, which reads 3, and the number, let's say 2, which is this one, aka 0, 1, then we will need to convert 1, 0 to 0, 1. 0 and 0, 1. Now we get into the second part, which is figure out which coin to flip. Which coin do we flip? Well, so we find the difference. We get, okay, so this has a difference of 1, and this has a difference of 1. So we know that we need to add 1, 1, right? So we find the difference between these two strings, which is 1, 0 and 0, 1, and then find the difference, the different bits, which is 1, 1. So we flip the fourth coin, which means this becomes 0. And now this board reads 0, 1, aka 2, the second square. The prisoner 2, after you flip the fourth coin, the prisoner 2 will see this board and say the number 2. So again, you get this board which reads 3, and then you're given the number 2, you flip the fourth coin, and now the board reads 2. And prisoner 2 will come in, read the board, and see the number 2. This, now we essentially have the entire solution, and we can extend this to 4 by 4, 8 by 8, 16 by 16, and so on. And the reason we use those because that's the number of digits. We add a digit to the bit, and it doubles. Actually, there's also, it also works with 32 squares, but it's not a it's not a square for this. So, but it does work for 32 squares. We add a digit. Technically, it works for any number, but because we're humans and not computers, visually, I want a square. And it's clean to show the maximum value for the binary string. It does work for any number. It's just more visually pleasing to have a square. Anyways, now let's say we have eight by 8. And for simplicity's sake, we're going to use more zeros than ones, right? Okay. Just to save time. Now, again, this represents 1, so we're going to be counting this way, and then this way, and so on for the square numbers, okay? This will be 1, 0, 1, 1, 1, 0, 0. This is the fifth square, but it reads 4 in binary. 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. This is kind of in the way. Let me move it up a bit. 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So again, this is 15 in binary, and this is 0 in binary. So it's 0 to 15 for the squares, 1 to 16. Now, this board, what does this read? Well, we're going to be using this document to keep track, so let me see. Here we go. What number does this board read? So we have 1 plus 101. Let me just align them. Plus 110 plus 1000 plus 1110. Because those are the numbers that have a heads up coin, or whatever we choose. Now, what does this add to? Well, here in the first digit, or in the leftmost digit, it adds to 0 because there's 2 ones. The second digit, it adds to 1 because there's 3 ones. In the third digit, it adds to 0 because there's 2 ones. And in the last digit, it adds to 0 because there's 2 ones. So this board reads 100, which is, as you can see here, number 5. It's foreign binary, but it represents the 5th square. Now, if the warden gives us a number that is 5, we will flip the first coin. If the warden gives us the number 2, or let's say he gives us the number 1, which is, you know, which is 0 in binary, because that's what this first square represents, which is 0, we're gonna flip the 5th coin, which, by the way, is always gonna be the case. If it gives you 1, then you're gonna flip the number that the board currently represents, because you're going to flip all of the bits. If the board currently reads 100, you're going to flip 100 and turn it into 000 by flipping the same coin, right? You have 5, you want 1, you flip 5. 5 is gone, you have 000. Now, so let's say it wants this one. Then we want the string to read 0001. The difference is 0101. So we will flip the 6th coin. Now you might see a pattern. If we want 10, if the warden gives you the number 3, then you're gonna want 10, and then you're gonna want 10, and you're gonna flip this coin. There you go. And now we're gonna say, let's give a random number. Let's say we want this one, 1010, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? The warden gives you the number 11. Oh, let me move this a bit to the left here. Gives you the number 11. We want 1010. Now what? We're flipping the first bit, the second bit, and the third bit, so we're going to be flipping the 110 coin, which is this one. We're going to be flipping this coin to convert 5 to 11. Well, that's the solution. You can extend it to any number of squares, and the 64 just adds 2 digits. You're going to be adding every heads up coin or tails up coin, whichever one you decide represents 1, and then you get the number that the board represents. Then you get the number you want the board to represent. You find the difference in the 2 numbers in binary, and then you flip the coin that is equivalent to the difference. In this case, it's this here. That's the solution. There you go.